All right, we begin this set of exercises by trying to construct Eulerian trail or cycle in this graph, or to explain why no such trail or cycle exists. So we look at the degrees of all the vertices, how many edges are connected to each vertex. 4, 4, 2, 2, 4, 2, 2, and 2. All of the degrees are even. If all of the degrees are even in your connected graph, you can construct an Eulerian cycle beginning wherever you want. Okay, so we're going to follow Fleury's algorithm, which says, look at all of the edges leaving the vertex you're currently sitting at. Don't follow any bridges unless that's your only option. And a bridge is an edge that, if deleted, would result in a disconnected graph. So if there are any bridges, try not to follow them. If you have no choice, then go ahead and do so. And the numbers on the edges are to make a slight modification. If you have multiple choices for where you can go next, always follow the edge with the lowest possible number. This means that the construction will be unique. So all students should get the same exact Eulerian cycle. We're going to start here. And we ask, I have two edges connected to where I am. Are they bridges? If I was to delete this edge, it would not make the graph disconnected. So this is not a bridge. If I was to delete this edge, the graph would not be disconnected. So this is also not a bridge. So edge 3 and edge 4, the only edges I can follow, neither of them are bridges. So to construct an Eulerian cycle, I could take either one, but with this modification, we take the one with the lowest number. So we're going to start by following edge 3. 3, there we go. Then we are now at this vertex, and I delete this edge from the graph. And we ask the same thing. Of all of the edges I can follow, 1, 7, and 9, are any of them bridges? If I was to delete edge 9, that would not make the graph disconnected. If I was to delete edge 7, it would not make the graph disconnected. If I was to delete edge 1, the graph would also not become disconnected. So all of them are options, and with this modification, we pick the one with the lowest number, so we're going to follow edge 1. I now delete edge 1, and I'm now standing at this vertex. Okay, the lowest number available to me is 2, so I may as well check that. If I was to erase edge 2, would the graph become disconnected? It would not. So since the lowest number isn't a bridge, I'm going to follow that. So I'm going to take edge 2, so I'm going to add that to my list. And now I delete this, and now I am standing here. Now observe, if I delete edge 6, the graph does actually become disconnected because this vertex will not be connected to anything else. So 6 is a bridge. However, it's also my only choice, so go ahead and follow it. So I delete this edge. I'm now standing at this vertex. And now that this vertex has been removed, I can kind of ignore it as well. The lowest number available to me is 5. If I was to follow edge 5 and delete it, I would disconnect the graph. Imagine if this edge vanished, then these two vertices would no longer be connected to the rest of the graph. In other words, 5 is a bridge. So I don't want to follow it unless I absolutely have to. So let's check the next higher option, 8. If I erase edge 8, the graph does not become disconnected. So this is not a bridge. So even though 5 is a lower number, it is a bridge, and I don't want to follow it unless I have no other option. But I do have other options. Edge 8 is not a bridge. So let's follow edge 8. Then I delete it, and now I'm standing here. Now my only option is to follow edge 7. 7 was a bridge. It disconnects that vertex, so let's ignore it now. Now I'm back here. My only remaining option is to follow edge 9, which is a bridge because it will disconnect this vertex, but that's my only choice. So now this vertex is done, and we followed edge 9. Now we're standing down here at the lower left. My only option is to take the bridge, which is edge 10, and then I can ignore that vertex from now on. I'm now standing here, and we took edge 10. My only option is to follow the bridge, which is edge 11, which removes this vertex from play and puts me back here. And now, finally, my only choice is to follow the bridge 5, removing this disconnected vertex from play. Over in my list, we followed 5. We're now back up at the top, and all we can do is follow the bridge 4. And there we have it. In the original, starting here, we made an Eulerian cycle by always following the edge with the lowest number we could, as long as it wasn't a bridge. So 3, 1, 2, 6, 8, 7, 9, 10, 11, 5, 4. There are, by the way, other Eulerian cycles that begin and end here. Fleury's algorithm does not give you the unique solution to finding an Eulerian cycle. There, in general, could be very many of them. With this little modification that the edges have different numbers on them, and we always follow the one with the lowest number that we can, however, that modification should make the solution, will make the solution, unique. So anyone who followed this modification will come up with exactly the same list of edges to follow. Once again, let's construct an Eulerian trail or cycle, or explain why no such trail or cycle exists. So how do I check if one even exists? We look at the degrees. 2, 4, 4, 4, 4, 1. Okay, so we have a vertex of odd degree. All right, that by itself is not much of a problem. 1, 3, 3, 5, 2. So there are more than 2 vertices of odd degree. So more than 2 vertices of odd degree. And I'll circle them in a second. This vertex, this one, and this one all have odd degree. So there is no Eulerian trail. There simply isn't a solution to find. Once again, construct an Eulerian trail or cycle. The first thing we want to ask is, can we? So let's look at the degrees. If all of the degrees are even, then we can start an Eulerian cycle wherever we want. If there are exactly 2 vertices of odd degree, then we can make an Eulerian trail that starts at one vertex of odd degree and ends at the other. And if there are more than 2 vertices of odd degree, it can't be done. So the degree is 4, that's even, no problem. Here the degree, however, is 5. 1, 2, 3, 4, 5 edges leaving here. Okay, this means if there is one other vertex of odd degree, I can make an Eulerian trail that starts here, and this is indicated as our starting vertex, and will end at the other vertex of odd degree, but I'm only allowed one more vertex of odd degree. Degree 2, degree 5. Okay, I now have 2 vertices of odd degree. By itself, that's not a problem. I can start here and then eventually end here, as long as I don't find any other vertices of odd degree. Degree 4, degree 4, degree 6, degree 4, degree 2, degree 4, degree 4. So every other vertex has even degree. So these are the only 2 vertices of odd degree. It is possible to construct an Eulerian trail that starts here and therefore must end here. And this was indicated as where we're supposed to start. So we execute our modification of Fleury's algorithm. Look at all of the labels on the edges connected to where you're currently standing. Determine whether they are or are not bridges. If you were to delete one, would it make the graph disconnected? Those are bridges. If it doesn't make the graph disconnected by its deletion, it's not a bridge. Of all of the things that are not bridges, follow the edge with the lowest number, move where you're standing, and then delete that edge. If, however, you only have bridges available, follow the one with the lowest number, delete it, and move on. So the lowest number available is 3. If I was to erase this edge, since it's duplicated by another edge here, nothing will get disconnected. So 3 is not a bridge, so we're going to start off following edge 3. We've now deleted this, and we are currently standing here. Then we play the game again. Okay, the lowest number attached to where I'm currently standing is 1. If it was to be deleted, nothing would get disconnected, so we'll go ahead and follow it. Now I'm standing here. We've got a 15, a 16, a 17. 15 is backed up by another edge anyway, so 15 is definitely not a bridge, so we'll go ahead and follow it. And now we're standing here. Okay, we can follow 2 as long as it's not a bridge, and it's not. If I delete this edge, nothing gets disconnected, so we'll go ahead and follow 2. Where'd my pointer go? There it is, 2. Okay, so we follow 2. We're standing back up here in the upper left. And so we ask, of all of the edges connected to where we are, well, there's only 4. 4 is a bridge. If this was to get deleted, this vertex would now be cut off from the rest of the graph. And we don't want to follow bridges unless we don't have any choice, and we don't. 4 is the only edge connected here. So we're going to go ahead and follow the edge 4. We're now standing back where we started, and this vertex, having been disconnected, should no longer be considered to be in play. Okay, we can follow 5, 6, or 22. Are any of these bridges? No, I can delete any of them without disconnecting anything, so let's go ahead and follow 5. Now we're standing here. My only option is to follow 11. It is a bridge. If I was to delete this edge, this vertex would now be stranded, but it's my only choice, so go ahead and do that. 11. I'm now standing here, and since this vertex has been disconnected, we kill it off. We're not worried about it anymore. Okay, from where I'm currently standing, our lowest option is 6, and that's not a bridge. If I disconnect that, nothing gets stranded from the rest of the graph, so let's go ahead and follow 6. Now I'm back to where I started. My only choice now is edge 22, which at this point is a bridge. As soon as I delete this edge, my starting vertex will be cut off from the rest of the graph, but it's my only choice, so we have to do it. We follow 22. It's a bridge. It strands my starting vertex, so let's ignore it, and now we're standing right there. Our options are 7, 8, and 9. 7 is not a bridge. Okay, if I were to remove this, it wouldn't disconnect anything, so let's follow 7. And now we're back here. My options now are 10 or 12. None of these are bridges. If I delete 10, I can still connect all the way around this way. So 10 is not a bridge, and it's the lower number option, so let's go ahead and take it. Okay, now we're standing here. 13, 14, and 9. 9 is not a bridge, so let's follow it. Okay, so now we're back here. 9, great. My only option is 8, which is a bridge, but it's my only option. So we're following 8. We're standing back here. This vertex has been stranded, but all of the edges connected to it have been used, so it's not a big deal. We're standing here. We've got 13, 14, 16. 13 is the lowest number. It's also a duplicate edge here, so it's definitely not a bridge, so we're going to follow 13. That brings us back down to this vertex. The only edge remaining is 14. 14 is a bridge. As soon as I delete 14, this vertex will become stranded, but it's the last edge connected to it, so no big deal. Kill that vertex. We're now standing back here. The only edge I can follow is 16. It's a bridge. At this point, at least, it's a bridge. If it were to be deleted, this edge becomes, or sorry, this vertex becomes stranded. No big deal, because it's the last edge connected to that vertex that we need to consider. So we're going to go ahead and follow 16, removing that vertex from play and sticking us back here. Okay, I have a couple of steps where I don't have much of an option. I have to follow 17, and then I have to follow 18. That will strand this vertex and then disconnect this vertex as well. So I'm going to do 17, 18, removing that vertex from play, standing me here, removing that vertex from play, putting me there. Okay. These are now 3 edges that all back each other up, so definitely none of them are bridges. So let's follow 19. That puts me here. 12 is the lowest number, but it is a bridge. If I was to use this edge and then delete it, these remaining bits would now be separated from the vertex that I land at. So since 12 is a bridge, I don't want to use it if I don't have to. 20 is a duplicate of 21, so 20 is definitely not a bridge. So since we have an option that isn't a bridge, do that. So we follow 20. Now we're back here. My only option is 21. At this point, 21 is a bridge, since we've already deleted these two things here. Once we delete 21, this vertex will become stranded, but that's not a problem because I'll have used everything connected to it. So we're going to follow 21. Now we're back here. Now that bridge of 12 is our only option. And we end up back here, and there's nothing else to do. We have used all of the edges. So with this modification of Fleury's algorithm and being told to start here, the edge list 3, 1, 15, 2, 4, 5, 11, 6, 22, 7, 10, 9, 8, 13, 14, 16, 17, 18, 19, 20, 21, 12 is the unique solution. Again, a Eulerian trail or cycle using Fleury's algorithm example. Let's check if it can be solved. Are there any vertices of odd degree? If so, are there exactly 2? Degree is 2, which is even, 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 even. All of the vertices have even degree, which means any vertex at all in this connected graph can be the start and stop of an Eulerian cycle, and we are indicated we want to do it here. Okay, so we just look at all of these edges. We're following the modified Fleury's algorithm. Fleury's algorithm in its unmodified state just says, follow any edge you can that isn't a bridge. If your only options are bridges, follow any bridge you want. Our modification uses these number labels and says, take the lowest number you can within those restrictions. Therefore, all students will get the same answer if they've executed it correctly. That's the only point here, is to make sure that everyone's getting the same answer. So the lowest number attached is 4. Deletion of this edge will not disconnect the graph. It is not a bridge. So we're going to start off using 4. And now we're standing there. The lowest number is 13, which is not a bridge. So let's follow 13. Now we're standing here. Now the lowest number available to us is 2. This graph, by the way, is very highly connected. There's lots of ways to get around. So we're not going to find bridges until we've done a fair amount of steps. So deletion of 2 will not disconnect anything. So let's follow 2. That puts us there. The lowest option is 3, which is also not a bridge. Puts us there. The lowest number available to us is 18, which is not a bridge. So follow that. The lowest number available to us is 6, which is not a bridge, so follow that. The lowest number available is 15, which is not a bridge, so follow that. The lowest number is 8, which is still not a bridge. Follow that. We're back where we started, no big deal. Okay, the lowest number is 5, which is not a bridge, so follow that. We started to use up a lot of the connections, so bridges might start showing up soon. Okay, we're now at this vertex here. 16 is not a bridge, so let's follow that. Now we're back here. 7, not a bridge, so follow that. All right, now we're standing here. Our only option is to follow edge 17. Edge 17 is a bridge now because once we delete it, this vertex will be stranded, but since it's our only option, we go ahead and do that. And now that this vertex has been stranded, let's just remove it so we don't worry about it anymore. We're standing here. Edge 25 is our only option. It is a bridge. Once we delete it, this vertex will become stranded, but since it's our only option, we have to do it anyway. So we follow that. We remove that vertex. We're now standing here. Edge 24 is our only option, even though it's a bridge. If it's our only option, go ahead and do it. Now that vertex is totally exhausted, so we can remove it. Edge 14 is our only option. So follow it. That vertex has been exhausted. We're now standing here. Edge 28 is our only option, so even though it's a bridge, we follow it. We're now standing here, and this vertex has been completely exhausted. Edge 1 is not a bridge. Okay. In everything that we have left, edge 1 is not a bridge, so let's follow it. edge 1. So now we're standing here. Our only option is now to follow 19. 19 was a bridge. It stranded that vertex, but that's okay. It's been exhausted. Follow edge 20, which is a bridge. This vertex has now been exhausted. We're now standing back here. Our options are 12, 22, and 9. Is 9 a bridge? Okay, it's getting a little tough to keep track of, but we still have these connections here. So all of this being interconnected makes 9 not a bridge, so follow it. We're now standing there. Let's add 9 to our edge list. Okay, is 10 a bridge? So we've got this vertex, that vertex, that vertex. We still have all of these paths and edges down here interconnecting, so 10 is not a bridge. We can still delete 10 without creating any disconnections, so we'll follow that there. 22 is now a bridge from where we're currently standing up here at the top, but it's also our only choice, so go ahead and throw in 22. We're now standing back here. This vertex has been exhausted, so let's remove it. Okay. Our only option is to follow 12. Then our only option is to follow 23. Then our only option is to follow 29. So we're going to do 12, then 23, then 29. Once we follow 12, we're standing here, but that vertex up at the upper center has been exhausted. Once we follow 23, we're standing here, and this vertex on the left has been exhausted. And once we follow 29, we're back where we started, and that vertex we just came from has been exhausted. So we're currently standing here. We only have 4 edges left. None of them are actually bridges, because we actually have this nice cycle here. So between 21 and 26, following our modification, we take the lowest number, so we'll follow 21. That brings us here. Now we follow 27. At this point in the procedure, 27 is a bridge. This vertex has now been stranded, so remove it from play. We're now standing here. Our only choice is 11, and then our only choice is 26. So once we did 11, this vertex was exhausted. Once we do 26, this vertex is exhausted, and we have returned to where we started. We did construct an Eulerian cycle. Okay, Fleury's algorithm, once you get the hang of it, is very, very automatic. There's just not much to it. Moving on, we're now going to construct minimal path trees with indicated roots. So the first thing we do is we copy over just the vertices, but not the edges. We're going to be running Dijkstra's algorithm. Our original edges are what we start off calling remaining. They remain to be considered. In the right, we're going to draw edges that we've used, and to begin with, we haven't used any of them. Red vertices are what I call questionable. They are things that have been connected to the root, and at the beginning, only the root has, because we haven't used any edges. White vertices are what I call distant. They are not yet connected to the root. So we need to begin by labeling all of these vertices with tentative distances. The root is distance 0 to itself. Everything else is functionally infinitely far away because they haven't yet been connected. You can label these with infinity or just an absurdly large number. It doesn't matter, as long as it's bigger than like all of these things put together, so it's definitely not a feasible way to get there. Okay, now Dijkstra's algorithm says, look at your questionable vertices, which to begin with is just the root. Find an edge that is remaining and try to use it if it's not already being used. So let's take this edge with a weight of 3. Now this gives us a connection to a vertex for the first time. This is no longer distant, it has now been connected up. And its distance is not infinitely far away, it's only 3 away. So I update that, it's not infinitely far away, it's 3 away. Now I do the same thing. Over on the left, I'll color this in, it's a red vertex now. Are there any edges connected to red vertices that we are not currently using? If so, pick one and put it in. Okay, how about this 9? Okay, that gives me my first connection to this vertex, so it's no longer distant, which means its distance isn't infinite. It took me 3 steps to get here, 9 more to follow this edge, so this vertex is now a distance of 12 away, and over on the left, I'll color it red as well. Okay, I'm going to be fairly inefficient about this just so we can practice the steps many times. Over on the left, are there any edges connected to a red vertex that we are not currently using? Sure, how about this 10 down at the very bottom? So tentatively, I'm going to put that in because it gives me a new connection to a vertex. So this vertex is no longer distant, it's now been questionably connected. So its distance isn't infinity. It took me 12 steps to get here, so 10 more makes this maybe 22 steps away. And again, in the interest of being really inefficient, let's try now using this edge, because it's now connected to a red vertex and I'm not trying to use it, so let's throw it in. 11. Okay, that brings this vertex into the mix for the first time. So it's no longer distant, it's now questionably connected. So it's not infinitely far away. How far away is it? Well, it took me 22 steps to get here. 11 more is going to make that a distance of 33. Okay. Now, are there any things I can add in over here? How about this edge, 7? One thing I like to do is to start this off just by connecting vertices however I can, and then I'll start worrying about trickier stuff. So this is no longer distant, it's been connected up. It took me 3 steps to get here, 7 more gives this a tentative distance of 10. All right. In the interest of connecting up what I can, let's go ahead and throw in this edge. 1 makes this connected up with a total distance of 3 plus 1 will make that 4. I can also throw this in with a weight of 6, bringing this vertex into the mix. It's now connected up with a weight of, and this is definitely going to change later, but 33 plus 6 makes this tentatively 39 units away. Okay, everything has been connected up, but there are definitely still edges remaining to be considered that I'm not currently using. For example, there's an edge here from this vertex to this one of weight 5. So let's put it in. 5. Does this give me a better way to connect existing things up? I could, for example, do 33 plus 5 to get here in 38 steps, but I already know I can get there in 4. So 4 plus 5 will give me a way to get here in 9 steps. That is better than 33. Okay, so what happens now? If you find a connection that is better than an existing one, update that distance. So instead of this being a distance of 33, it's going to be a distance of just 9. As soon as you update the distance to something that was already connected, delete every edge connected to it, except for the one that you just put in. Okay, so I'm going to go to delete all of the edges connected to that except for the one that I just put in. Okay, I'm not doing anything to the graph on the left yet. The only time you delete edges from the graph on the left is if in the instance you attempt to use an edge, you decide that it's not better for you. Okay, so let's test something out. This edge was labeled 11 and I deleted it. Let's try putting it back in. So I put it back in with an 11. It connects 2 existing vertices that were already connected. So 9 plus 11 would make that 20, and that's better. So I'm going to update this score to be 20. Once I update an existing connection, I have to delete every other edge that was connected to it. Having deleted that edge, I might say, let's try putting it back in. 10. Okay. 12 plus 10 is 22. That's worse than this. 20, I already know I can get there with 20. And 20 plus 10 is 30. That's worse than 12. So in the very instant I try to add this edge in, I immediately decide no. This is the scenario where you say, okay, this edge did not help, and I just tried to put it in. In the very so-called round of action in which I attempt to put in an edge I decide not to, that's when I remove it from my list of remaining edges. Okay. This edge here, let's try it. 8. It connects two vertices that are already red. 10 plus 8 would make 18. That's worse than 9. 9 plus 8 would make 17. That's worse than 10. So I'm not going to use this edge. And I've made that decision exactly when I tried putting it in for the first time. So that's when I delete it from the graph on the left. Okay. Let's take this edge. This edge had been in there earlier. Let's try putting it back in. 6. Well, now 9 plus 6 gives me a faster way to get there. That's just 15 units away. So having updated the score to a vertex, I should delete all of the other edges connected to this except for the one I just put in, but there aren't any. All right, looking over here, are there any edges remaining that I haven't yet used? Here's a 2. 2 is a low-cost edge. I should have tried using that a while ago. All right, 2. 15 plus 2 is 17, much worse, but 4 plus 2 is only 6, much better. So I can get here using only 6 units. Now, anytime you update the score to a vertex, delete every other edge connected to it except the one you just put in. So I'm deleting this from my set of used edges, I'm sorry. But this isn't the first, like the moment I tried using it, so I'm not deleting it from the left. You only delete from the left if in the very same moment you try to use an edge, you decide you're not going to. But having deleted it, maybe I say, let's try putting it back in. Let's try using it again. Now, 9 plus 6 is worse than 6, and 6 plus 6 is worse than 9. So in the very moment I attempt to use this edge, I decide I'm not going to, so I'm not going to use it, but since I made that decision at the moment I tried using it, now I can delete it from my list of remaining edges. Okay, are there any edges that remain that I haven't used? There's this one, this 4. All right, so 0 plus 4 is a tie. I already have a way to get there in 4 steps, or I have a new one. Generally, if you have a tie, the easiest thing to do is not use it. You can make any choice you want. You can decide to use it, but I'm just going to decide not to. It doesn't save me any effort. So let's not complicate things. I'm just not going to try it. And since I made that decision the very moment I attempted to use this edge, I delete it from the list of remaining edges. And now we see there are no edges that remain that I'm not already using. This is the moment when you're done. Here is our minimal path tree rooted at the given vertex. When you have these moments of decision because of ties, that suggests that the minimal path tree is not unique. So there might be multiple different trees that are minimal path trees. What will, however, be unique are these labels on vertices. I could have gotten here in 4 steps either by doing 3 plus 1 or just by doing 4. So I might end up with a different tree, but this label of 4 was uniquely determined. Another minimal path tree problem, we copy over our vertices but no edges. Remember that I'm keeping remaining edges on the left. I am attempting to use edges on the right. Red represents vertices connected to the root. White represents vertices disconnected from the root. And at the beginning, we only have the root. Okay, so I start off with a distance of 0 here. My disconnected vertices are effectively distance infinity away, but those are always going to be updated, so I'm not even going to bother writing it down. Now let's look, are there any edges connected to a red vertex that we're not currently using? Sure, 13. That brings this in for the first time, 13 units away. Are there any edges connected to red vertices that we're not currently using? Sure, 14. Since that connects two existing connected vertices, I ask, does it actually make anything better? I could already get here in 13 steps, so getting here in 14 steps is objectively worse. So I am not going to use it. I delete it from the used set. Since I'm deciding not to use it in the very instance I attempted to use it, that's when I also delete it from my set of remaining edges. I'm never going to try using it again. Now I just keep going, okay? Any edges connected to red vertices that I haven't already used. As I've mentioned, I sort of like to connect things up to new vertices whenever I can. So I'm going to do this with 15, and I'll go ahead and do this with 11. All right, that gets me some new vertices into play. It took me 13 steps to get here and 15 more, so this is going to be labeled with 28, and that's just going to be labeled with 11. All right, any edges connected to red vertices, let's color these red on the left for record-keeping purposes. Any edges on the left that I haven't used, sure, I could try this one. 13 plus 16 is just worse than 13 plus 15. So this edge of 16, in the very instant I try, I decide, nope, so I'm not going to use it. And since I made that decision in the same round I tried to, I know I'm never going to use it. Okay, how about this 12? 13 plus 12 is 25, that's worse than 11, and 11 plus 12 is worse than 13. So that edge doesn't actually save me any effort. And since I'm making that decision to remove it in the very same moment I tried to use it, I know I'm never going to use it. Okay. Are there any edges connected to red vertices that I'm not already using? Only this one. So let's go ahead and put it in. 10. It took me 11 units of distance to get here. 10 more makes this 21 away. This vertex is now connected up. Are there any edges connected to red vertices that I haven't already been using? Yeah, there's this one, 8, there's this one, 7, there's this one, 9. That's going to bring all of these vertices into play with a total distance of 29, 28, and 30, respectively. Okay, on the left, let me just color those in red so I can keep track. Are there any edges connected to red vertices that I am not currently using? Let's attempt to use this edge of weight 6. So I'm going to go ahead and put that in, 6. Since it connects two things that were already connected, 29 plus 6 would get me here in 35, but that's worse. 28 plus 6 would get me there in 34, but that's worse than the 29 I already have. So that edge doesn't help me. Let's delete it. Since I decided not to use it in the very instant I tried, I can remove it from my original graph. I know I'm never going to use it. All right. From here, I can follow an edge of weight 2 or an edge of weight 3, both of which get me to new places. So that connects up my last remaining vertices. Good. Since that's the first time they're connected, I'm definitely going to use that edge for the moment with a 31 and a 32, respectively. Looking over on the left, are there any edges that I'm not currently trying to use? Sure. This edge of weight 1, let's put it in. Since it connects two existing, two vertices that were already connected, 32 plus 1 would be worse than 31. 32 plus 1 would be 33, which is worse than 31, but 31 plus 1 is a tie. Last time we had a tie, we decided not to use it. Let's just see what happens if we decide to use the tie. Okay, so this 31 plus 1 ties the 32 we already have, but we're actually going to keep that. We're going to use the new connection, which means delete the old connection. But I didn't make this decision to delete that edge the very moment I tried it, so I am not going to delete it from the list of remaining edges. Maybe I try putting it back in right now. Well, 32 plus 3 is worse than 29. 29 plus 3 is a tie. You can get into a bit of a loop here if you keep using the ties. Okay, so maybe I would keep this and throw that out. Then I would try to use it and keep this and throw this out. Then I would put this back in, etc., etc. So in order to avoid this possibility of looping, you can be clever about it, or you can simply decide to never use a tie. Anytime you have a tie, consider it worse and don't use it. So that's what we'll do from this point forward. Anytime we see a tie, we're not going to use it. So this 3 gave me a tie score here, and from this point forward, we are never going to use any ties, so I'm not going to use it. Since I made that decision in the very round I tried, nope, we're not going to keep it. Okay, now I only have 2 more edges to consider, a 5 and a 4, so let's put the 4 in there. 32 plus 4 is worse, 28 plus 4 is a tie, which we've considered to also be worse, so I'm not going to use that edge. Since I made that decision in the very moment I attempted to, I go over to the graph on the left and I delete it. I'm never going to try. The only edge left to consider is this 5. but now it's even easier. 32 plus 5 is worse. 28 plus 5 is worse, so we're not going to use that 5 either. And since I made that decision when I first tried to, I know I'm not going to use it ever. So I remove it from the graph on the left. And now the graph on the left and the graph on the right are the same, and that tells me that we're done. We found a minimal path tree. Okay, from this point forward, anytime we find a tie, we're not going to keep it, specifically to avoid the possibility of an infinite loop. Another problem, minimal path tree, we copy our vertices, remaining edges on the left. As we use edges, we'll put them on the right. Red edges are connected to the root, white vertices, are not. So we start off with a distance of 0 here. Everything else is effectively infinitely far away. And then we just ask, are there any edges that remain connected to red edges that we're not currently using? Sure. This edge, 5. This edge, 6. This edge, 22. And let's throw in this edge, and I'll use the one that's labeled 4 just to make a point. So these are all our first connections to these vertices, which means they are no longer distant. They're now questionably connected at a total distance of 4, 22, 6, and 5, respectively. Then I can come back here and say, oh, maybe I should have tried this edge. So let's put it in. Since it connects to already connected vertices, I try both directions. 4 plus 3 is definitely worse than 0. 0 plus 3 is better than 4. Okay, so that's actually better. So I'm going to not use that edge, and I'll update this to be distance 3 away. Even though I deleted this edge, it was not in the round of action that I put it in. So I don't delete it from this graph on the left yet, but let's do that again. Let's try putting it in now. And we quickly see, oh, that's worse. So I'm going to delete it. And since I'm deleting it in the very so-called round of action that I tried to put it in, I am going to delete it from the graph on the left. This is no longer ever going to be considered. I might try also this edge labeled 11. 6 plus 11 is worse than 5. It's bigger than 5. 5 plus 11 is bigger than 6, which means, nope, I'm not going to use that edge. And since I decided not to use that edge, as I was first attempting to, over on the left, I know I'm never going to use it. All right, what other edges can I put in? Maybe this 7. Okay. This 7, 6 plus 7 is less than 22. So update that. Then delete this edge. Maybe it will end up being reinserted later. I find pretty good practice to be, as soon as you delete an edge that was already in there from several steps ago, try to put it in right away, because maybe you get to delete it forever. So let's try putting it back in, 22. Since it connects up two vertices that were already connected, 13 plus 22 is worse than 0. 0 plus 22 is bigger than 13, so I immediately decide, nope, I'm not going to include this edge. Since I made that decision in the moment I first tried, I go back to the original graph and I say I'm never going to try using it. Okay. Any new connections I can bring in are usually helpful. So from this vertex here, I've got a couple very low weight edges that bring me to new vertices, so let's put those in. Those are likely to be kept for a long time, if not forever. So that brings two new vertices into play. We've got 3 plus 1 is going to be a 4 label here, and 3 plus 2 is going to make that label 5. Whoops, let me erase that errant pen mark. Also, that's not a 5, it's supposed to be a 4. Okay, so I label this with a 4. All right. Now let's look at these two edges here, because I'm pretty confident I'm not going to want to use them. So let's try to introduce the 16. 5 plus 16 bigger than 4, 4 plus 16 bigger than 5. That means I am not going to use this edge. Since I made that determination when I first tried to use it, I know I'm never going to use it. The same thing, without bothering to write it, if I put this edge of a 15, 5 plus 15 and 4 plus 15 are both objectively worse than what I already have, so I'm not going to use that edge either, so let me just delete it here. All right. Here I've got an edge labeled 8. Let's attempt to use it. Since I'm connecting two vertices that were already connected, I try both directions. 13 plus 8 is bigger than 5, so no. 5 plus 8 is 13, that's a tie, and we've decided to never use ties. So I'm not going to use this edge, and since I made that determination when I first tried to use it, I know I'm never going to use it. Okay. This 6 I can connect up here with a 10 and here with a 12. That's going to bring two new vertices into play. With what weights? Well, here I had 6, so 10 more is going to make that 16, and 6 plus 12 is going to make that 18. 16, 18. All right, any internal connections that I'm pretty confident I'm just never going to use? Yeah, this here, this connection of 9, this edge, 13 plus 9 is bigger than 16, and 16 plus 9 is bigger than 13. So that edge, the very same instant I try to use it, I know I'm not going to. That's when I get to delete it from my original graph. Similarly, here I've got 13 and 14. Those are connecting here. But 5 plus 13 or 14 is going to be bigger than the 16 I have here. 16 plus 13 or 14 definitely bigger than 5. So one at a time, if I add this in with a 13, I immediately say, nope, I'm not going to use that. So I delete it. And since I deleted it as I tried it, I get to delete it from the original graph. And similarly, if I throw this in with a 14, I would immediately say, nope, nope. So since I'm not going to use it, delete it. And since I deleted it as I first tried to use it, delete it from the original graph as well. All right, what else can I now do? We can put in this edge with a weight of 17. That's our first connection here for a total of 4 plus 17 is 21. Okay, that's now connected. And now here, I've got a 19, a 20, and a 21. So let's first connect this up with a 19. It's our first connection, so for the moment we're going to keep it, with a total of 18 plus 19 is 37. Now I'll try it with a 20. That connects two vertices that were already connected, but 18 plus 20 is higher than 37, and 37 plus 20 is way higher than 18, so I'm not going to keep it. Since I decided not to keep it the very same instant I tried, in the original graph on the left, I know I'm never going to use it. Similarly, if I tried to connect these with a 21, that's just higher cost than 19. So I would throw it in, I would check both, I would decide to delete it, and then in the original graph, I would go ahead and not use it. Are there any edges remaining on the left that I'm not currently using? There's only one. There's this, 18. It connects two vertices that are currently being used. 21 plus 18 is larger than 37. 37 plus 18 is larger than 21. So I immediately say, no, I am not going to use this edge. Since I made that decision right as I tried, I can delete it from the original graph. And now the graph on the left and the graph on the right are the same. So we have found a minimal path tree rooted at the given vertex. And for our final problem, the same thing, a minimal path tree. We copy our vertices, remaining edges on the left. As we use edges, we'll put them on the right. And again, we start off with a distance of 0 at the root. Everything else is effectively infinitely away, but since those are guaranteed to be changed later, I'm not bothering to write them. We ask, are there any remaining edges in the graph on the left connected to red vertices that I haven't used? Well, the first thing I'm going to do is I'm going to look for connections to new vertices that aren't part of a multigraph, that aren't redundant connections. And this isn't a multigraph anyway, so that's not going to be a concern. So I'm just going to throw in 1, 2, 3, 4, 5, 6 edges all at once. This edge, 29, gets me here in 29 steps. This edge, 21, gets me here in 21. 26, 5, 8, and 4. These vertices are all now questionably connected. Probably, I'm not going to keep all of these edges by the end of the problem, but for now I am. We've got a lot of interconnection between these vertices, so let's test some of them. For example, this 13, let's try putting that in there. 13. And we see, whoops, I forgot to label this, 4. that this 4 plus 13 gets me here in only 17 steps. So that's better. Whenever I update the distance to a vertex that was already connected, delete all of the other edges connected to it, only from the used edges. I don't delete them from the remaining edges. But whenever I delete something from used, if it's still remaining, let's try to put it in right away. And aha, this 0 plus 29 is worse, 17 plus 29 is bigger than 0. So in this instance, I see, as I attempt to use the edge labeled 29, I'm not going to. So I delete it, and since I made that determination right away, that's when I get to delete it from the original graph. Okay, this is a pretty cheap edge, and so is this. So I'm going to try one and then the other. If I put in this 2, that's my first connection here for a total of 19. But now I'm going to throw in this 3. And we see that this 21, it's not written very well, sorry, that's not a 4, that's a 21. It came from this edge. 21 plus 3 is larger than 19. 19 plus 3 is larger than 29, so I am not going to keep the edge of weight 3. And since I made that determination right as I was trying to put it in, I'm actually never going to put it in. Even though it's a very cheap edge, it's only 3, it's not going to belong to any minimal path tree rooted at the given vertex. Okay, let's see. We've got this edge here, 14. Let's test that out. 4 plus 14 is larger than 8, and 8 plus 14 is larger than 4, so I'm not going to use this edge. And since I figured that out right away, I get to delete it from the original graph. This edge here, 24, similarly, if I test putting it in, 8 plus 24 is bigger than 5, and 5 plus 24 is bigger than 8, so I immediately determine I'm not going to use that. Since I made that determination right away, I know I'm never going to use it. How about this edge right here, 16? Well, when we put this in, we see that 5 plus 16 is actually less than 26. So I update that with its new distance of 21. Since I have updated a distance on an already connected vertex, I delete every other edge connected to it. And as soon as I delete an edge that has been in there for a while, I like to immediately try to put it back in. Because now we see, aha, 0 plus 26 is worse, 21 plus 26 is definitely worse, so we can immediately rule that out. And since I decided not to use it in the very same round that I put it in, I get to delete it from the original graph. All right, let's connect some new vertices. From here, I can use this 6 or this 7. That brings these in for the first time with a total of 27 and 28, respectively. Over on the left, I'll connect those up. All right. But here's an edge, 15. Okay, this edge down here. 8 plus 15 is less than 27, so I'm going to update this with a 23, which means I need to delete every other edge connected to that vertex. And having deleted that edge, I'll immediately attempt to put it back in. I'm attempting to put it back in right away because if I'm not going to use it, and I make that decision as I'm attempting to add it, that's when I'm going to get to delete it from the original graph. And I'm trying to cut down on the original graph as much as I can. So we just added this edge. 21 plus 6 is bigger than 23. 23 plus 6 is bigger than 21. So nope, I'm not going to use that edge. And since I just attempted to use that edge and decided not to, that's when I get to delete it from the original graph. We could try now this 17. 23 plus 17 doesn't beat 28, and 28 plus 17 doesn't beat 23. So we are definitely not going to use that edge. And since we decided that right away, I'm going to go ahead and delete it over there. Let's see, what else do we have down here at the bottom that we can test? Sure, we've got this edge labeled 25. Okay, so this edge here, we'll go ahead and copy in. It connects two existing vertices. 5 plus 25 doesn't beat 23. 23 plus 25 definitely doesn't beat 5. So I decide right away that I'm not going to use that edge. And if I'm not going to use that edge and I decide so right away, I get to delete it from the original graph. Okay. Moving on, what do we got? We've got this edge here, this 18. I'm pretty sure we're going to get rid of that. So if I connect this with an 18, indeed, 21 plus 18 doesn't beat 21, and 21 plus 18 doesn't beat 21. So since I decided right away not to use it, I get to delete it from the original graph. Now let's go ahead and throw in this 11. It's our first connection to this vertex, so we're going to keep it for the time being guaranteed. 21 plus 11 gives us a tentative score of 32. But I also have this edge here, 27. If I throw that in, it connects two vertices already connected. 21 plus 27 does not beat 32. 32 plus 27 does not beat 21. So I immediately decide, nope, I'm not going to use it. So I erase it. And since I made that determination as I was attempting to put it in, I get to erase it from the graph. Okay, let's test this guy here, labeled with a 9. We're using this edge now. 19 plus 9 does beat 32. So I update this with a 28. Having updated a score, I erase every other edge connected to it. Since that wasn't the moment I first tried to use that edge, I don't get to delete it from the graph on the left, but as I've mentioned, what I like to do is if I delete an old edge, I immediately try to put it back in. 21 plus 11 does not beat 28. 28 plus 11 does not beat 21. So I am, in fact, not going to use this edge. And since I just attempted to, I get to delete it from the original graph. All right. What else do we have going on? Let's try this. 28. First time reaching this vertex. So it's definitely going to be used for the moment. And I give it a score of 32. Let's use this edge. It's a 1. It's the first time I reach this, so I'm definitely going to use it for the time being, giving it a score of 33. And I'm just trying to connect everything up. I'm using this edge, which was a 19. 33 plus 19 gives us a tentative score of 52. And from the 19, I can use this edge, 22, connects this for the first time with a score of 41. Okay, everything's connected up, but now let's just look for things over here that I haven't put over here. This 8, this 5, I think the bottom is all used up. Here, this edge 23. Let's try that out. So I try to connect these with a 23, but 32 plus 23 is bigger than 17, and 17 plus 23 is bigger than 32. So I'm not going to use that edge. Having made that determination right as I was attempting to put it in, I get to delete it from my original graph. This 12, let's try that. 12. Okay, and here we actually see 19 plus 12 is less than 32. So I found a better way to get here, which means I need to delete every other edge connected to it, including that one up there. Okay. As soon as I delete an edge, I ask, maybe I can immediately put it back in. We actually deleted 2 edges, so let's do this one at a time. First, let's try to put the 28 back in. So here is where our 28 goes. If I attempt to reinsert that, 4 plus 28 does not beat 31, and 31 plus 28 is definitely bigger than 4, so we immediately decide not going to use it, and since we made that determination right away, we're never going to use it. Now let's try putting this 1 back in. 31 plus 1 is less than 33. So update this score to 32. Having updated the score to a vertex that was already connected, erase every edge connected to it other than the one you just used. Since I just erased that edge, I'm going to attempt to put it back in. 32 plus 19 is 51. Having updated this score, I should delete any other edge connected to it, but there aren't any. Okay, let's look back over here. The 4, the 13, the 2, the 12, the 1, the 19. I think this 20 and this 10 are the only thing left to try. Let's start off with the 20. and we find 19 plus 20 is actually less than 51. So this gets updated with just 39. Having updated that vertex, I delete every other edge connected to it. Having deleted that edge, I'm going to immediately try reinserting it. 32 plus 19 is bigger than 39. 39 plus 19 is bigger than 32. So just as I'm attempting to reinsert that edge, I decide I'm not going to use it, which means I can delete it from the original graph. Sorry, all of these vertices should be red now. And I believe the only edge left to consider is this 10. So let's try putting it in. 10. 28 plus 10, in fact, does come in less than 41. So this gets updated with a distance of 38. Having updated the distance on a vertex that was already connected, I delete every other edge connected to it. Having deleted an edge, I'm going to attempt to immediately put it back in. 22. 19 plus 22 is larger than 38, and 38 plus 22 is larger than 19. So I delete that edge, and since that was right as I was trying to put it in, I get to delete it from the original graph. And at long last, our original graph is now exactly the same as the graph we've constructed on the right, so we have found a minimal path tree rooted at the given vertex. So the fastest path to this vertex is 39 by going 4 plus 13 plus 2 plus 20. The fastest path to this vertex is a total of 38. 4 plus 13 plus 2 plus 9 plus 10, etc. This was a fairly long example because there were a lot of vertices and a lot of interconnections between them, but eventually we figured it out.